Okay, in this tutorial, I'm going to show you some nonlinear curve fitting techniques. From a practical standpoint, we won't delve into the theory, and I'll do it in 4 different languages: Matlab, Mathematica, Python, and lastly, R. Okay, well, the first thing we're going to do is to import this data from the Excel file testdata.xls, which is a set of x values and y values to be fit to a nonlinear function. Okay, so here is the Matlab code that will fit that function. I can go through and show what the commands are doing step by step. Maybe it's useful to just run this right away. And so let me do that. I'll run this by command return, and now a plot has popped up showing the data as squares and the best fit in blue, along with what was my quite poor initial guess to fit that data. So let's go in step by step and show how this works. Okay, so what I'm going to do is I'm going to start by running select pieces of this code. First thing I'm going to do is I'll close all my variables, clear my variables, close plots, and read in the data. And this code right here reads in the data and then ascribes 2 variables, the x values, y values, c and v. Let's go ahead and run that. So I'm going to run that using typical MATLAB commands, and here I can see that they've been run. So here C is my maybe concentration data, V is some kind of a velocity data, and then I will just use an input value for the error, which will become more clear later. It's just 0.01 for now. And now what I'm going to do is I'm going to plot the data. This next line plots the data. I'll bring this into the view, and there's the data being plotted. Next, I'm going to define a fitting function, and the fitting function is basically this function here. V as a function of C, like concentration, and in terms of 2 parameters, V max in front and K. So this is a nonlinear function that I want to fit. And I've just basically written it up here as a function of C, concentration, and a vector P, which has 2 components, P1 and P2. So I'll define that. And now that's been defined. There. Now this is just to make a kind of linear space of concentration between a minimum of 0 and a maximum of C. And then the next line is going to provide an initial guess for the parameters in that function above, which I'm just taking to be 0.1, 0.1. Almost any guess will do. And then I'll plot my initial guess. Okay, so on my computer, this command will be function shift F7, and you'll see I've just plotted my initial guess, shown here in the dotted line. Now I'm going to define a fit function, and the fit function, as described here, is a weighted sum of squares of the residuals. And the residuals are the y values of each data minus the function value, in this case starting at the value of the dotted line. And that's my definition. And here it is, here you can see y minus the function squared divided by my constant error of 0.01 squared. Let's go ahead and define that function. And now with that function, that error function defined, I want to minimize it. And the command to minimize it is fminsearch. And I'll define some options. And one of them is to just display the output iteratively, and then a tolerance function, which is typically a small value. Okay, and now I'm going to use my fminsearch function, which takes this fitting function and it expects a set of parameters that is fed into it. That's the p here, the first argument, which is starting off at p naught. It'll then take the options, and then it'll take the x values, because it's expecting the x values, and then it'll take the y values of the data as the y values. This will then output the best fit parameters, capital P, and the final function value, and an exit flag that's 1 or 0, depending whether it ran correctly or not. So let's go ahead and run that now. It runs very quickly, and the error decreases monotonically from a large value to a small value, and the parameter output is given by the vector p as shown here. So I'll type it again. Here's p. Good, so there's my parameters that I have now found. So that's very different than my initial values, which were 0.1 and 0.1. And so now we can plot our result. I'll plot the result, I'll add a legend. Okay, and here finally is my result. Okay, so in Mathematica, the commands are fairly similar. First thing I'll do here is clear all my variables, and then I'll simply set the right directory to where my data file is. And then this next command is to import our test data from the Excel file and assign it to a variable data. And there it is as a list, a paired list. And I can render this if I want as a grid. I'm simply typing Shift Return to enter these commands. Here are the X values, here's the Y values as a grid. And now I will plot the data. Here's a list plot of the data, X versus Y. Nothing fancy here. I haven't labeled the axes or anything, just to show the data and see what the scale of the parameters might be. Then the next step is to fit this to a function. But the first thing I'm going to do before I do that is I'll define the function. Here it is, v as a function of c, and my parameters, v max and k. And I can do something interesting in Mathematica, which is a function called manipulate. I'll plot this function, and I'll allow these two parameters to vary. K and v max are going to vary, and I've just set some ranges that I'm going to vary them over. So let's take a look at that. So now I've got this a plot of this function with k set to, I guess, 0.01 and v max 0.015. Those are the bottom limits of these parameters. And now what I'll do is I'll just use these scroll bars to kind of adjust the values of k and v max as I like. And so I see here I can't quite fit this data with these two values, but maybe if I turn this down a little bit, maybe I can turn this up a little bit, and I can get a pretty good initial guess there. Actually, that's pretty close to the actual optimized values. In that way, you can use this tool in Mathematica to get a good guess for the initial values. And then the function in Mathematica is called nonlinear model fit, and it simply fits the function v to the data. And I can also put in some restrictions on the range. So I knew, for example, that I wanted k to be bigger than 0, but less than 0.05. I didn't want it to go too high. I didn't think it should have been higher than that. And Vmax I also thought should be less than 0.25. It can be anywhere smaller than that, but it shouldn't be bigger than that, because I can see that 0.25 is way above the asymptotic limit of the data. So, for example, those are restrictions on the parameters. And it looks like it found the fitted model, and there it is with the values inserted. If I want to see them, I can use this. I set this whole thing to nonlinear model NLM, and then here's the parameter table of k and v max, along with errors and some statistics. And I can actually look at those best fitted values for Vmax and K-fit, 0.2114, 0.0173, and I can compare that to my Matlab values that I had seen before, 2114, 0173, and they are essentially the same fitting values as we saw before. And now finally showing the data and the best fit plot on the same plot. And you can see that that looks remarkably similar to the plot that I had obtained in Matlab. So there we go. That's how you do it in Mathematica. Okay, so in Python, I'm not an active Python user, so this code was written by Lucas, and I had to modify it a bit for our purposes here in the tutorial, and I'll step you through the code. So first thing we're going to do is clear our variables, and looking up how to do this, this is how one clears variables. I'll then import the operating system, some mathematical function capabilities, then specifically in the scientific Python libraries, I'll import a function called curve fit, and that's where we're going to do our nonlinear curve fitting. Here's a plotting library, and this command is to close any open plots. So I'm going to run all that, and as you can see, variables were all cleared and all plots were closed. So now we're starting. I'll set my directory to where my input file is, and there it is, my printed directory. Fine. Okay, so now I'll open the data and assign the variables. And here's my data. Here's C, concentration, and V, velocity. And now I'll define my fitting function. And now I'll use my optimization to find the optimal parameters and the covariance here, which is not used. This is just for error analysis. And now let's take a look. And you can see that these are similar but not identical parameters to what we had seen before. It probably has something to do with our tolerance functions, which I'm not going to go into detail to check. So I'll now make a plot of my best fit function. And probably I should have plotted the data first, but anyway, here's the data plotted and a legend. Okay, so there's the, oops, getting cut off. There's the data and best fit along with the parameters. So this is how one would code this up in Python. Okay, in R, the code would look something like this. These first two lines clear all the variables that I might have had open and close all the plots, which I've just entered. Okay, the next line is a optional nonlinear models package that has extra options that I don't think we need for our tutorial. The next two lines will set the working directory to where my data is and then print it out. And you can see here in the command line, it's now set to the directory that I want it to be. And the next thing I'm going to do is to read in the data, which is going to be in a CSV file that I'll show now. Okay, here is my CSV file consisting of 7 numbers of concentration C and say velocity V. And just like we had seen before, there is a header on the file here. Okay, so now I'm going to read in the data from that file. And this line reads in the CSV data saying that there is a header using comma separated values. Reading it in now. And now I see that it's been read in. I can take a look at the entries over here, or I can use a command called view in R, and this now shows the same data that I had shown you before. Next, I'll define basically some limits of the plots that are useful for plotting. And then what I'll do is I'll make a plot of the concentration values and these velocity values, label the x-axis, label the y-axis, label the plot as nonlinear fit, set these x limits using the values that I had just defined here and here, and plot it. So now you'll see the plot once I execute these commands. So there it is. There's the data. And now what I'd like to do is to fit that to my nonlinear function, shown highlighted here. Okay, and this function is a function also of the parameters Vmax and k, which I would like to find. Next, I will use the nonlinear least squares function, or NLS, with this functional form in there. V has this functional form, and I've just typed it in there. And for the data to be fit, I'll use the dat that I have loaded, and that's a list or structure of data that I've loaded. Then I'll set my initial values to 0.1, and k is 0.1. I've done something very similar in Matlab using those initial values. And here we go. So let's enter that command. There we go. It's basically found it, and it has a whole bunch of variables inside. We can look at a summary of what the nonlinear model contains now. So this nonlinear model structure contains, here's the formula, and here are the best fit parameters, 0.2113 and 0.0172. And you might see that that compares well with the values that we had seen in Matlab or Mathematica or Python. I can view these parameters in a nice sort of pretty interface shown here. And going back to the code, now what I'm going to do is it's all just comes down to plotting it. And I'm going back to the plot here, and I'm going to define a vector that begins at 0, ends at the number c end, and has 50 elements in it. So I can plot my best fit on a finer grain rather than the coarse-grained data that's in here. So I'm now going to set kind of 50 x values to plot the best fit function to. And so this best fit functional form is then basically asked to predict what y values it would get if I put in those x values for cc from this vector. And so that's what this line does. And then this last line will plot it. cc, the nonlinear model function, blue, line type is a straight line, a solid line. Line width is set to 2. That's what those options mean. Here we go. And so now you can see a nice best fit curve for these best fit parameters Vmax and k. And that's how you would code this up in R.